Today we're going to be talking about the universal law of gravity and doing a class discussion on it. Just a heads up, this class discussion does have the answers filled in on it already, and the purpose of that is just to kind of speed things up here a little bit so that we don't have to spend a bunch of time working problems. Instead, I can just kind of explain what's happening and hopefully keep this video relatively short. So right away, to start off, all objects that have mass are actually attracted to each other with a force of gravity, believe it or not. Now, the force of gravity is actually a very weak force, and the reason why it's such a weak force is because if we look at the formula for the force of gravity, it's F equals this big G times the mass of one object times the mass of the second object divided by the distance squared between them. The reason why the force of gravity is so weak is if you look at G, the value of G is 6.67 times 10 to the negative 11th. That's a super small number. So when you put that super small number in here and multiply it by stuff, it turns out that the force of gravity becomes very small. Unless you're talking about supermassive objects, and an example of a pretty massive object would be like the Earth. So the Earth does provide a relatively large force of gravity because it's just such a big object. But say you and I, even though we are gravitationally attracted to each other, the force between myself and you will be very minimal because our masses just aren't very big, and then this G is such a small number. When you multiply by a small number, it turns out that the force becomes very small. Questions I will usually ask about the universal law of gravity is more so relationships between the force and the distance between an object and the force and the masses between objects. So I have a little if-then chart, I call it, and I recommend writing this down. So what this is saying is if the mass increases, the question I would ask you would be, well, then what happens to the force? So if the mass goes up, then the force goes up. If the mass goes down, then the force goes down. And these are examples of what's called a direct relationship. Basically, whatever the mass does, the force does. Okay, so if the mass goes up, the force goes up. If the mass goes down, the force goes down. Okay. The other question I could ask you would be, if the radius increases or goes up, what happens to the force? Well, if the radius goes up, the force goes down. If the radius goes down, then the force goes up. And this is called an inverse relationship. Okay, whatever the radius does, the force does the opposite. Something to watch for is this radius is squared. Okay, so if the radius goes up by a factor of 2, the force isn't going to go down by a factor of 2. Instead, it's going to go down by a factor of 2 squared, which 2 squared would be 4. So if, for instance, the force was let's just make it really simple. Let's say the force was 8 newtons, and the radius increased by a factor of 2. You'd take 2 squared, which would be 4, and so the new force, I'd take 8 divided by 4 would be 2 newtons. Okay, notice how much of a drop that is. All right, that's something that is hard to wrap your mind around. I get that. It's something people struggle with often, but there will be questions that kind of exactly test you on that. Okay, so keep that in mind. And I kind of go into a discussion about that, talking about how that if the mass was double, the gravitational force would double. If the radius was double, the force would be quartered, and so forth. And you can see this kind of cool relationship between the gravitational strength and the y-axis, and how as distance increases, it would continue to get smaller and smaller and smaller. Okay. So here's a question for you. This one actually deals with numbers, where it asks, what is the gravitational force of attraction between two asteroids in space, both with a mass of 50,000 kilograms, separated by a distance of 3,800 meters? So all I did in this problem, and I apologize I didn't write the formula, I just used Newton's universal law of gravity, which says F equals big G times the mass of one object times the mass of the second object divided by the distance squared. All right, and I just plug numbers in. Big G is 6.67 times 10 to the negative 11th times the mass of asteroid 1, which they said was 50,000 kilograms, times the mass of asteroid 2, which is also 50,000 kilograms, divided by 3,800 squared. One thing I highly recommend you doing is practice punching this in on your calculator and see if you get a force of 1.15 times 10 to the negative 8th. Or another way of writing that would be decimal point, 7 zeros, and then 115. If you aren't getting that number, I probably can't help you right now in the video, but you should come and see me so that we can play with your calculator a little bit, because you're probably punching something in wrong on your calculator, and that is the number one mistake with these types of problems where you have to actually punch numbers in, is it's just calculator errors that people just aren't putting their exponents in correctly. So please come see me if you aren't getting this answer correct, okay? Let's continue on our journey here. As a meteor moves from a distance of 16 Earth radii to a distance of 2 Earth radii from the center of the Earth, the magnitude of the gravitational force between the meteor and the Earth becomes blah. Well, if we go back to kind of thinking about our if-then chart, we're going from 16 Earth radii to 2 Earth radii. So the radius is going what? Down. If the radius goes down, then the force must go up. And this is just a real generic statement, okay? So we will want to be thinking about things where the force is going to increase. So anything where the force is decreasing, such as number 1, automatically we can eliminate that. Now that doesn't help us that much. We still have 3 options where the force does increase. Which one is it? But using that method, sometimes you can get rid of an option or 2, and that kind of helps. Even if you're going to guess, at least makes your guess a lot stronger. But we can actually do this. 16 Earth radii to 2 eighth radii, that is a factor of 16 divided by 2. That would be a factor of 8, okay? Of 8. So basically, the distance has decreased by a factor of 8. Now remember, in Newton's second law, the radius piece is squared. So I'm going to take 8 squared. And if you take 8 squared, that gets you 64, right? The force of gravitational attraction is going to be 64 times stronger or greater than when this object was 16 Earth radii away from the Earth. Pretty crazy, isn't it? How that squared really makes that big of a difference. But that is actually the answer. So that'd be number 3 in this option. If you're not getting that yet, don't worry. There's some more problems I have to practice this. 2 objects gravitationally attract each other with a force of 18 newtons. If the mass of one of the objects is doubled, and the distance between their centers is doubled, then a new force of attraction is blank newtons. All right. I kind of take this as a step-by-step approach. If we go back to our if-then chart, if the mass goes up, what happens to the force? Because that's the first thing that says happens, is the mass of one of the objects is doubled. Then the force must go up, right? Because it's a direct relationship. What about with radius? It says that the distance increases, right? So the radius, right? It says distance between the centers doubles, yes. The radius goes up, so what must happen to the force then? The force must go down. Okay, so kind of keep that in mind. All right, we're going to have some of it going up, some of it going down. Let's first take on the mass piece, okay? We have a force of 18 newtons. The mass doubles, right? So I'm going to take on this number and I'm going to double it. The force is going to double. So how do you double something? Just times it by 2, and that's written right here. 18 times 2 equals 36, okay? So if the problem just stopped there and said, if the mass doubled, what would the new force be? You would say 36 newtons. Done, all right? Problem is that the problem doesn't do that. Instead, it says that the distance between them doubles, okay? So it increases by a factor of 2. Remember, the radius is squared in Newton's universal law of gravity. So I have to take 2, because that's the factor that it is increased by, and square it. What is 2 squared? Well, that's 4, right? And that's why I take 36 and I divide it by 4. And the new force of attraction would be 9 newtons. That would be your answer. Right. These types of problems are a lot more likely to be seen on tests and quizzes than, say, the problems where you have to punch in a whole bunch of numbers and basically use your calculator. To me, this is more valuable that you understand how to do this than, say, just punching numbers into a calculator. Okay, so just a heads up, this is kind of what I'm expecting you guys to be able to do compared to the previous previous 2 problems ago, or whatever that was. All right. Last question. 2 objects gravitationally attract each other with a force of 18 newtons. If the masses of both the objects are doubled and the distance between their centers is doubled, the new force of attraction is blank newtons. Okay, let's first deal with the mass piece. You have both of the masses of these objects doubling. So not only one doubles, they both double. And so if the mass increases, the force is going to proportionally increase. And so I'm actually going to take 18 and I'm going to multiply it by 4. Which I did right here. 18 times 4, that equals 72. If that was all the problem asked, you'd be done. You'd say 72 newtons is the new force of attraction. The issue is that the problem says that the distance is also doubled. And remember, in Newton's second law, r is squared. So I'm going to take 2, because that's the factor by which it increases, and square it. 2 squared is 4. So I'm going to take 72 divided by 4, and that gives us 18 newtons, which is actually the same thing that we started with, but that actually is the answer. It would be 18 newtons. that takes care of this class discussion. Hopefully you guys have a better understanding about Newton's universal law of gravity. As always, if you have questions or comments, feel free to see me in class or shoot me an email. We'll see you guys later.